Hello, Algebra 2 students. Hopefully you did not end up in a sugar-induced coma from all of your Valentine's candy and you are well. Anyway, I appreciate you finding time to get your notes taken care of. These will be the last set of notes going towards our next unit test, which looks like it will be on Wednesday. The final thing that we need to do is we need to look at the difference between square root functions with equalities, which is what we've been doing all along, and now look at them with the possibility of them being inequalities. So please copy down your title, Inequalities and the Square Root Function, as well as your objective. And our objective for this day is the student will learn, should be to determine how an inequality affects the solution set for a square root function. As always, anytime the video gets going too fast for you, just hit pause. When you get caught up on your notes, then you can hit play and move on. Okay, so let's get started. Now, the obvious of this situation is, of course, for years you have been studying graphs, and we should probably have a pretty solid idea by now that in an equality, any point that exists on the curve of the graph, and by curve I mean any type of a graph, a line, a parabola, a square root function, a logarithmic function, any of the things that ever show up in a graph, if a point exists on that curve, okay, then that point is a solution to the equation for that curve. In other words, we can take that value, x comma y, we can plug it into the equation in place of x and y, and the equation, whatever it says, should be true. Whatever the left side equals should be exactly the same thing on the right side. Now, when equalities change into inequalities, it kind of muddies the water a little bit. Okay, not only do we have to worry about the curve itself being possibly part of the solution, but now we have an area of space in the graph where any point that exists in that space is also a solution for that graph. So that's going to be our focus today, is to take a look at these graphs and see if we can figure out when we are greater than or less than. Also compare and contrast greater than, less than, to greater than or equal to, less than or equal to, and refresh all of this stuff in our heads. This is things we've all done before. The only difference is using the square root functions rather than regular lines and stuff like that. Let's move on. Okay, so let's start off with an example here. Okay, now this is a similar equation to stuff that we have been looking at for the last week, week and a half. Y equals the square root of x minus 2 plus 3. Now what we said is any point, okay, any ordered pair that actually does exist on the graph of this square root function, okay, is a solution. That x comma y can plug in to the equation and make that a true statement that the left side does actually equal the right side. And as we have explored here in recent days, we know for a fact that there are infinite solutions to an equation, so infinite ordered pairs, infinite points that are on that graph. Okay, so I picked on 3 whole numbers. Okay, in this particular graph, 2 comma 3 is a solution. When you plug in 2 for the x and 3 for the y, you will end up with a true statement from that equation up top. Same thing with 3 comma 4. Same thing with 6 comma 5. Okay, and of course, you know, you have imaginary, not imaginary, but irrational values in there as well. Lots of decimal points because of that radical in the problem. Okay, so clearly I've just listed a few of the possible solutions here. There are infinite numbers of solutions, and many of them will contain irrational numbers. Now, what we're looking at today is, okay, what happens if we take that equality that we were looking at the top of the page and make it an inequality by installing something like a less than symbol, like we have right there. Okay. Now, the graph of this guy, okay, you can already see the graph of the equality up top. But the graph of this one, not only do we get the equation itself, the curve itself, but we also get shading one direction or the other from the graph. Now please notice that just like the equation does not continue through the entire graphing screen there, because some of the values are real, some of them are imaginary. So our graph does not continue through the entire screen. Our shading will not continue through the entire screen either. Okay, so the curve that we looked at from above, now it bounds in an area that is full of solutions. Okay, well, the skill that we're going to be working on is, okay, how do you actually decide which direction to shade and stuff like that? Okay, now there are different ways to deal with the inequalities, or to manage the inequalities, to understand what it is that the inequality says and how to graph it and stuff like that. So some of this may be review for you. Okay, but it's something we're responsible for, so even if it is review, copy it down. Let's refresh our memories. Okay, sometimes we are going to have to determine which direction a graph should shade away from a curve. Okay, now it's not a difficult concept. Okay, some of it can be very, very simple. Okay, some of the equations we have been seeing are already in a form where they have a variable isolated. If this is the case, okay, that a variable is already isolated, this is very easy to determine the direction to shade of the inequality. Okay, if a variable is already isolated, you can simply shade in the direction of that axis according to which way the inequality is positioned. Okay, I've got a couple of examples here that I'm going to do for you. Okay, have a look. We have an equation that says y is greater than the square root of negative x minus 2 minus 1. We have a variable that is already isolated, and it happens to be y. Okay, so that tells us that we are going to be shading in the y direction. We're either going to shade straight up from this graph, or we're going to shade straight down from this graph. Which direction do we shade? Well, what does the inequality say? Y is greater than this graph. Well, if y is greater than this graph, where do you find the values of y that are larger than this graph? Obviously, they are above it. So you would shade above, but you would not extend out past the vertex. If the equation itself cannot extend past negative 2, then neither can your shading. Okay, but there it is, really very simple, reading it straight out of the equation. Here's another one. X is less than the square root of y plus 2. Okay, well, we have a variable already isolated, so we can just allow the equation to tell us which direction to shade. Okay, in this case, the variable that is isolated is x. Okay, that means that we're going to be shading in the x direction, so we're either going to go from this equation straight to the left, or we're going to go from this equation straight to the right. Okay, which direction should we go? Well, the equation says x is smaller than the square root of y plus 2. Okay, where are the smaller values for x located at? Well, they are located to the left. So from that graph, we would shade to the left. And once again, we will not extend any further down than the vertex. If the vertex cannot go, or the graph cannot go any further than that endpoint, then neither can our shading. Now, what have we discovered? Okay, anywhere in those green areas that we just colored on the graph, okay, any point that you find in that space is something that will solve these equations. You can plug any point that's in there in the equation, and it will give a true statement. Now, obviously, this worked out very well as long as the variable was isolated, but what happens if the variable is not isolated? It's a simple thing to do if the variable is isolated, so you can bet the people that write test questions against us, they are probably going to make some of them so that it is not that convenient. Okay, so obviously, if the variable is not isolated, one of our options would be to isolate it. Okay, pick a variable and isolate it. And I put if it is possible or if it is practical to do so. And what that means is, we can look at equations like this one. Okay, y would be very easy to isolate in this instance. All we would have to do is add 1 to both sides of the inequality, and y would be isolated. Very easy to get that y by itself. Okay, or something like this. 2y is greater than the square root of negative x minus 2 minus 1. Again, very easy to isolate y here. All we would have to do is divide the entire inequality by 2, and y would be isolated. No big deal. On the other hand, a problem like this, okay, I think we would be halfway insane to try to get one of those variables isolated. Okay, our algebra skills are just not quite that solid. And on top of that, there are some sticky points in there. When we start taking square roots and squares of variables, we start ending up with that plus or minus option, and there's just a lot of things that can go wrong. So here's an instance where, you know what, we probably would not try to isolate y or x in this particular case. Okay, there's just too much algebra in the way. Okay, now if you have one that you cannot isolate, like that third option there, then here is kind of the fail-safe. Okay, you can pick a test point in open space, plug it in, and see if that makes the statement true or false. Okay, and this is actually one of the kind of the mainstay methods, just like the plotting method is one of the ways that we tackle unknown equations. Picking a test point is a very widely accepted way of going about deciding which direction to shade with an inequality. Okay, if you pick a test point and plug in, and that gives a true statement, then what the problem said to you is, yes, I like that point, shade toward it. Okay, on the other hand, if you pick a test point and plug it in, okay, and that gives a false statement, then the equation is again communicating with you, saying, no, 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 I don't like that point, okay, do not shade towards it. So you would shade the opposite direction. And we have a third possibility that we've probably never run into before now, but we've already seen it this unit. Okay, plugging in values, sometimes we end up with non-real answers. We get some imaginary statements, negatives trapped underneath radicals that we cannot deal with. Okay, so if you pick a point and you plug it in, and by plugging in, it causes the problem to go imaginary, what that means is you are in an area that cannot be shaded one way or the other. Okay, so you'll want to pick a better point, probably something closer to the curve, and then see what happens. Okay, and when I say pick a point closer to the curve, here's pretty much what I'm talking about. Okay, you know that the square root function looks like half of a parabola, so it's got a curve. If you will pick a test point that is kind of in the cradle of the curve, okay, so you will probably find a true statement or a false statement, and you will very seldom come out with an imaginary statement. Okay, but here's a graph. Okay, this blue one happens to be y minus 3 is less than the square root of negative x plus 3. And let's say instead of isolating the y, you just said, hey, I'm going to pick a test point. So we picked on this yellow guy right here, negative 3 comma positive 4, and plugged in negative 3 and 4 for the x and the y. Then what we end up with is a statement that says 1 is less than, and it comes out to approximately 2.45. So is that true? 1 is less than 2.45? Okay, actually, I've got an incorrect statement in my notes there. I don't know what I was thinking there. Okay, 1 is absolutely less than 2.45, so that is true, which means shade toward. Okay, so from the curve, okay, we're talking about a y value, so we would shade in the y direction toward that point, since the equation did like that point. So I apologize for the error there in the notes. Anyway, let's take a look at a couple of examples here. Okay, graph the solutions for, and we are given an equation. Or actually, an inequality, not an equation. Okay. Let's see if we can't get this guy into the graph. Okay. Now, we always have the ability to do the plotting method. We can pick several points in the domain and plug them in one after the other and see what the y value says, and we can plot our points that way. Okay. However, I think we ought to be able to get a pretty reasonably accurate graph using the skills that we've come up with in the last week or so. Okay, so let's look at our vertex, h comma k. Okay, in this particular case, we have our h value. It shows to be a positive 1, but it should have been a minus in the problem, so that would be minus 1 on the h. The k shows to be positive, but it's supposed to be positive, so that is a 3. Okay, but there's what we've been talking about here lately. There is a sign change with the variable that is underneath the radical. That means that we need to also change the sign for the h value. So we thought it was -1, but the reversal of the x-axis is going to change it back positive. So we have a vertex, and our vertex is at +1, 3. Okay. Now we've already said that our graph is going left because of that sign change that is underneath the radical. There is no sign change on the radical itself, which means our graph is still moving upwards. We have a speed value coefficient there of 2, meaning the graph is going to raise up twice as fast as it should have. Okay, so let's see if we can't get this. Let's get this going here. From the vertex, it is going up and to the left. Now, as it moves 1 unit over to the left, the parent function would move 1 unit up, okay? But our graph is moving twice as fast, so it should be 2 units up. As we move 1 more step over, the parent function would move up 1.4, but ours is moving twice as fast, so it should be 2.8. As we move 3 steps over, the parent function moves up 1.7. Ours is going twice as fast. That would be 3.4. Okay. Another step over, the parent function would move up 2 units. Ours is moving twice as fast, so it would be 4 units. So pretty clear of where the graph is headed. Okay, and let's look at how we should draw this line. Now remember, with inequalities, there's 2 different ways to draw the line, the curve itself from an inequality. There are solid lines and there are dashed lines, and the difference would be a solid line is an answer where that curve is part of the solutions. It needs to be included. That would be an equal sign with the inequality. But we also have dashed lines, meaning that is a boundary, but the line itself is not part of the solutions because you have a non-equal inequality. Right now, we have an equal inequality because of the equal sign. So we can pretty confidently draw our graph something like that. Now let's figure out what direction to shade it. Okay, we have an equation where we have a variable already isolated. The y is already isolated, so we are either going to shade upwards from this graph or downwards from this graph. Okay, which direction should we shade? Okay, the equation says y is less than this curve. Okay, so where are the values of y smaller than this curve? That would be downward. So we kind of get a boundary right there underneath the vertex, and all of this area in here would be shaded. Any point in that shaded area, including the line, would satisfy this inequality. Let's look at another. Okay, this one is an inverse. Okay, we have, looks like x is going to be isolated by itself. Everything else is going to be on the other side. Okay, so pretty easily we can isolate this. Let's see what we need to do in order to get it isolated. First thing I would do is I'd say, you know what, that +4 doesn't need to be there, so I'd move it to the other side of the problem. Okay, that would give negative x is greater than negative of the square root of y minus 2. Now remember that +4 is a whole number constant that came over. He cannot enter in underneath that radical and join with that -2. It's not the way it works. We are almost isolated here. We have a negative x. We don't want a negative x. We want a positive one. Okay, so we basically want to change the sign of x. And the way that you do that is basically to either multiply or divide the entire problem by a negative sign. That will reverse all of the signs of the main terms. Okay, so the negative x will become a positive x. The negative square root of y minus 2 will become a positive square root of y minus 2, and the positive 4 will become a negative 4. Now, the one thing I'd like to caution you on or remind you on is this guy right here. The algebra of working with an inequality is exactly the same except for one thing. If you ever find a reason to multiply or divide an entire inequality by a negative value, then that will reverse the direction of the inequality. So while it used to say that x was going to be the larger side of the problem, now it's going to say that x is going to be the smaller side of the problem. And missing that one key step right there can absolutely cause you to miss an entire problem. Okay, so x is isolated. Now, I'm going to move this guy up out of our way. Okay, there is our new equation we're going to work on from there. All right, let's get a vertex. Okay, obviously our vertex is h comma k. Okay, so let's get it out of the problem. H in this particular case is negative 4. K is positive 2. No need to do any sign changes because the variable, the y, underneath the radical, does not have any sign changes. So negative 4, positive 2, our vertex sits there. Okay, let's have a look at the speed. The speed is regular speed. Okay, direction, our y is going to move upwards just like it should. And our x value is going to move rightward, just like it should. But remember, this is an inverse. Okay, most of our normal equations, a y equals square root, is going to start upward and then turn outward. Okay, well, this is an inverse. The inverses start moving outward and then they turn up or down. Okay, so we already know it's heading up. Let's see where its points would be. So on the parent function for an inverse, as you move one unit away from the vertex, which in this case would be up, okay, it should move one unit out. As you move 2 units away from the vertex, it should be 1.4. 3 units away is 1.7. 4 units away is 2. And again, these are all just values that are accomplished by plugging into the parent inverse function. Okay, now let's check on the direction that we should shade. Our equation says x. Okay, x is the value that's isolated, so we are either shading directly to the left or shading directly to the right. Okay, the problem says x is smaller than the graph. Okay, so where are the values where x is smaller? Clearly, they are to the left. Okay, now, one thing. I drew this graph a few minutes ago, and I wasn't really thinking about it when I did it, but look at how I drew the equation. I drew a solid line. Solid line would suggest that the line is part of the solution, but look at the equation. Does the equation have an equal sign attached to its inequality? It does not. So this line that I've got right there, I'm going to take that guy and get rid of him. I should have drawn a dashed line. He is the boundary for that graph. Okay, the boundary for the solutions, but he is not actually part of the solutions because there was no equal sign in the inequality. Okay, one final example. The graph below is incomplete. Determine the correct line and shading for it. Okay, well, we've been fortunate on the previous 2 examples where we've been able to isolate a variable, and that is a pretty easy way of determining which direction to shade. Okay, now we do not have that luxury. The equation is fairly complicated. Okay, we would have to move a lot of stuff over the inequality in order to get the y isolated, which is what would need to happen to get our square root function. Okay, so what we're going to do in this case is we are going to, first we're going to draw our line. We're going to decide if it should be a solid line or a dashed line or what. Okay, so what do you think? Solid line or dashed line? Well, look at the equation. If it is an equal inequality, then that will be a solid line. If it is a non-equal inequality, then that is a dashed line. All we have is a greater than sign. So this guy is going to be dashed. He is the boundary for the area that is going to be shaded, but he is not included as part of the solutions. Okay. Now, we don't really know what we're looking at as far as which direction we're going to shade, obviously. But let's look at the nature of the curve here. Okay, we kind of need to figure out, is this a standard graph or is this an inverse graph? Okay, well, we need to know that first off, the regular parent, the standard parent function, it starts mostly upward and turns outward. The inverse, on the other hand, starts mostly outward and turns upward or downward. Okay, so we need to decide, is it a standard graph or is it an inverse graph? Because if it's a standard graph, then we are talking y equals, and the shading would be either upward or downward. If it's an inverse graph, then we're talking x equals, and the shading would be leftward or rightward. Okay, so let's have a look. Okay, now you can see down in this part of the graph, there's a fairly pronounced curve right there. Now this graph is in a big hurry, its speed is high, but there's a little bit of a curve down there, a greater curve than what you see up here. Okay, that's an important thing to be able to notice, because that means that at this vertex down here, it is basically heading upward and then turning outward. If it's going upward and then turning outward, then that means the graph we are looking at now is a standard y equals type of graph. So when we shade, we're going to be shading upward or downward from the graph. Now, which direction do we shade? Okay, well, that's the question. Now, what we need to do is we are going to need to pick a test point in space and plug it in. Okay. Now, we know that we're going to be upward or downward, so we definitely do not want to pick anything out here, because none of that is even in consideration. If you plug that into the problem, you're probably going to end up with an imaginary number. So we definitely want to pick either above the graph or below the graph. And you can pick any value that you want, so you might as well make it easy on yourself. Pick a point that's easy to manage, okay, something like this, -2, 0. Keep the numbers small, so when you plug them in, you can kind of tell what's going on. So let's see, 1/2 times the y value, in this case the point I picked has a y value of 0, plus 2 needs to be squared, and the question is that greater than -4 times the x value, which is -2, plus 2. Okay, so let's simplify here. Half of nothing is nothing, plus 2. Okay, nothing plus 2 is 2, and 2 squared is 4. Okay, so we are curious if this is greater than whatever's happening on the right side of the problem. Okay, well, over here, -4 times -2 is +8. 8 plus 2, obviously 10. The statement says 4 is greater than 10. Is this a true statement? This is not a true statement. 4 is not greater than 10. So the equation just told us, no, I do not like that point. Do not shade toward that point. So we will shade away from that point. Okay, that's basically the way this works. I absolutely apologize for the length of this. It just takes a little while to kind of talk our way through it. Anyway, we'll see you in class and see if we can't practice some of this stuff out.